thanks, Steve. Thank you for the opportunity to come back and talk to you guys. As Steve said, I've been doing this for a few years now out here, but if you pick my accent, I'm Australian. Been living in the US for the last 10 years. Been working in the US for probably the last 15 years. I'm living over in St. Louis, Missouri, in the center of the country, but I've spent a lot of time here in the Panhandle. So started coming over here in 2009 and helped introduce soil moisture probes to many of you guys. There's quite a lot of previous customers sitting out amongst you, and I've had a great time doing it and learning. Apologies up front, a lot of my slides are a little dated because Russ Hodges, who talked at lunch, took over from me in this area, and so he's been running with things for probably the last 5 years, or I've been doing other things and working for other companies. Just real quick as an introduction, GroGuru, I'll tell you a little bit more about that as we go through what we're about, but I am a soil moisture probe guy, irrigation agronomist, and I got pretty excited with an opportunity to take capacitance probes and put them underground and transmit data from there. So that's really what we're about with GroGuru. So this is an area where we started doing that cable-based 5 years ago. We tried to put probes underground and it didn't really work. Now we've got the technology to do that. So you'll hear more about that, I guess, around the place. But I didn't come here for an advertisement. I came here to teach you guys about soil moisture sensors for the first session, and then I want to teach you about how to use them. I need the clicker. So, yeah, as I said, I'm going to just split this up into a session on basically the hardware, and then we're going to talk more about the what do you do with it, how do you make money out of it. And so I'm going to, thankfully, the previous speakers today, especially Jordan, Pat, and others, have really set the scene for me in terms of basic terminology and that sort of thing. So we can get through some of this pretty quickly. So as far as terminology, we'll talk about methods of measuring crop water use, and then go on to look at different sensors in the market. And then this is a pretty important part, where do you place them? And then another really important part of this is not just where do you put the sensors in the field, but where does the water go in relation to the sensors? Or where do you put the sensors in relation to where the water goes? Because these days we're getting water really close to the ground, we're bubbling it on there, we're not wetting all the soil anymore, we're wetting parts of the soil. And so sensor placement gets really critical, as you'll see. So, as funnily enough, Pat actually used the same slide, so we've been shopping on the internet in the same place. Yeah. So I don't need to dwell on it, other than to say, water sticks to the surface of soil particles. Okay, we're coating the soil particles, and so once you've coated, let's talk about wetting a pot. If I put and I've done this before as a demo, take a pot of dry soil, and I take out a watering can, and I pour water on there. If it was glass and you could see what's going on, you'll see it wetting down through the soil. What's happening is we're coating the soil particles until so water sticks to those, and then water's filling up the interpore space, and so you're basically moving from this first point here where it's coating the soil to having soil filling up the pore space to a point where it can't hold anymore, and so gravity takes over and it goes to the next level. So we think about this as layers of sponges. So it's sort of wetting from the top down. So let's assume that we let all this drain through and let the pot dry out, and you come back to that pot tomorrow, the next day, and it's still wet. There are no plants in there, but now I take my watering can and I put red dye in there, and I pour red dye, water with the red dye into that pot. Water's going to come through pretty much straight away. Why? Because I've coated all the soil particles. Okay, so now what happens is there's nowhere for this red water to stick, so it's actually goes straight through, and so it goes out the bottom. So what comes out the bottom, I pour it on the top, what comes out the bottom is pretty much red straight away. And so think about that if you're putting fertilizer in your water. But it's important to know how water is held in the soil. So then we can talk about how the plant takes it up, and Pat did a good job of that in terms of using all the easy, so gravity's taking the excess water, and the plant's using what's not bound really tightly. So then we've also had a slide similar to this, talking about different soil moisture, different amounts of water in the soil, and how hard the plant has to pull to get that out again. And so that fill capacity by definition is how much water the soil can hold against gravity. So, and it's by definition, it's 24 hours after you've saturated the soil, what's left in there is fill capacity. So if I take my pot and I've saturated it, I've wet it all the way through, water's draining out the bottom, 24 hours later, what's in that pot is fill capacity. Then I'm going to be able to use a certain amount of water. I get to a point where the plant cannot pull water away from the soil. So it's adhered to the soil more, like so tightly, that the plant can't pull it away. So the plant dies, which is why it's called permanent wilting point. So between what the soil can hold against gravity and what the plant can't pull out, we've got available to the crop. And the rule of thumb is that the first half of that is readily available. The plant doesn't have to try very hard to pull it away. And then the second half of that, so the bottom half of the gas tank, as it were, the plant has to exert some level of pressure, or it goes to some effort to pull that water away, and that effort gets harder and harder and harder the closer you get to permanent wilting point. So that's why now you could argue at what line this managed allowable depletion, we call it, this at what point does the plant, is it 50%, is it 40%, is it somewhere, is it 30%, where is that number? Well, as I'll show you when we use these tools, the plant can actually tell you that. You don't have to work it out, you don't have to use theory, you just have to watch the plant and it will tell you how, at what level it's starting to go into stress. So we just talked about having excess water and so on, but I want to now start to bring in the measurement tools. Actually, quick survey. Who is now or has used soil moisture sensors of any type? Hands in the air. So pretty much most people. I guess flip that around. Who hasn't used soil moisture sensors? We've got a few people. Okay. Go back in the day. So the first sensor that was really widely applied or used was a gypsum block, closely followed by a watermark sensor, which is a better version of a gypsum block, because these things literally dissolved in the soil. And watermark sensors hung around, will last a lot longer. Or we've got tensiometers. But what are we doing? We're actually measuring how much suction the plant has to put on the soil to pull water away from it. And so if water is freely available, then there is no tension at all, up to a point where the plant has to exert quite a lot of suction on the soil to pull the water away from the soil surface. So there's a lot of research done over the years to get magic numbers, as they were, to say once we get over this amount of suction, the plant's going into stress. And so those magic numbers are pretty well refined for certain crops over the years. You go up to Nebraska and everyone has been I guess the University of Nebraska has some great research done, Land Grant University, on how to teach people irrigation scheduling, and they got out there with watermark or tension measurements, and that's been the language up there for a long time. So even more so than capacitance probes. But that's really what we're talking about, is how much, if there's water freely available, it's easy, the plant's happy. And then as we have to apply more suction, the plant gets to a point where it can't pull any more moisture out, and it's a stress level. So what that looks like on a graph is the reverse of what a probe looks like. Because as the soil dries out, the tension increases, it's flipped. So a high tension is actually dry soil, because the plant's having to think of it like pulling on a syringe or something. You've got to exert a lot of suction to get water off dry soil. And so in this case, there may be two sensors, one at one at 1 foot and one at 3 foot, let's say. And we can see here, when they irrigated, the tension went down. So as I said, you've got to think in reverse, but in the lower sensor it didn't hit that. So when we get a deep irrigation, we can see that both of these sensors went down. So that's how you use tension measurements. But some of the disadvantages of tension, it takes a while for the sensor to equilibrate. So it's not instantaneous. You can't see when wetting fronts hit certain layers. when there is no tension, when the soil is wet, tension drops to 0. Well, is it wet and it's stable, like field capacity, or is it wet and it's draining, like when I was pouring water on that pot in my first example? You can't tell if drainage is happening. All you can say is that the plant has no problem pulling water out when the tension is 0. So you're missing a little bit of information there. And of course, other sensors can measure temperature, they can measure salinity and other things depending on what kind of sensor you've got. So you're missing out on some other information. Watermark sensors or tension measurements work in a ball. So the measurement zone is a ball. It's measuring up and down and out and round to the side. It measures a good amount of soil, so that's good. But it takes a while for that to equilibrate, and you don't get, the reason we tend to put them at 1 foot and 2 foot and 3 foot is because if you went any closer, the measurement zones would overlap. And so you don't get that stratification that you'll see we'll get in other sensors. So then we go to volumetric soil moisture, VSM, you could call it VSW, volumetric soil water measurement. So there's lots of different sensors out there that measure the quantity of water in the soil. So as Russ pointed out at lunchtime, you irrigate, soil moisture goes up on a graph. It's a gas gauge. You can, so it's sort of more intuitive. And you can see there's different, so we've got, this is a Neutron Probe. That's actually a radioactive device. This is actually the research gold standard. I cut my teeth as a summer intern on Australian cotton farms, swinging one of these things around, taking measurements every day. And so that's what I did for 3 summers running, which is how I ended up doing what I'm doing, I guess. But it's got, you put these tubes, empty tubes in the ground, and you basically carry this thing around and lower a sensor down, and you take measurements at different depths. And you go around, usually every site, sort of, I don't know, every couple of days, every 2 or 3 days, and you can plot the change in water use. The reason it's a gold standard is because it measures a really large volume of soil. And so it's really robust. Year in, year out, you don't have to worry about installation or anything like that. In fact, I'll get onto that on my next slide. So we've also got these other ones that have got little spikes on them. And so they are, essentially there's capacitance sensors, but there's a couple of different kinds. There's ones where we set up a radio frequency in the soil, which is like here, where you've got these rings, and so you've got sets of rings. Think of them like radio antenna that send radio waves into the soil. It's electromagnetic waves, but essentially you're tuning it to how much moisture is there. And then as you increase or decrease the amount of moisture, it slows the speed, it changes the frequency at which the waves oscillate. So the best analogy I can think of is that it's like tuning into a radio station on the old manual radio. No one's got one anymore, and maybe you've got an old pickup. But you tune into a radio station, and then you'd add moisture to the soil, and so it would change the frequencies. You have to go down the dial and retune it in to that radio station. And how far down the dial you've gone is how much moisture is there. So that's one way. It's called frequency domain capacitance. Or we can have waveguides where we send a pulse down these waveguides, and it measures how long the pulse takes to go down and come back, and the amount of moisture that's there slows down the speed at which that moves. So that's called time domain, because we're measuring the time. So there's different ways, there's different sensors, there's all kinds of things, there's different companies that do it. And so if we go on and look at these in detail, as I was saying, the Neutron Probe, it's measuring a really large volume of soil. I mean, it could be literally, if the soil's dry, we could be going out 18 inches from the source. And what it does is radioactive, so you need a license to use it. You don't want to hug it, you want to sort of hold it out here. The reason it's in a big box is because that's actually filled with paraffin wax, which absorbs. What it's doing is it's sending out neutrons, and the neutrons hit hydrogen atoms and they reflect back, and then it counts up how many reflected neutrons there are. Well, water is H2O, so you've got 2 hydrogen atoms for every oxygen atom in the molecule. More water, more hydrogen, more water, bigger count. It's actually pretty robust because it's measuring a really large volume of soil. And so people use those in research trials because you can go from one year to the next year to the next year to the next year, and the numbers all mean something. You can relate one to the other because it's a pretty rugged device. But The graphing is done in a weird way. You look at basically you take your readings going down through the soil, and then you actually use a calibration here. It's worth calibrating. In fact, you have to really make it work, because you're coming out and taking readings every few days, so you can't watch yourself getting to a certain number. You actually calibrate it against soil moisture volume. But the fact that it's radioactive, it's a lot of people, when I first hit the industry and I was carrying this thing around, you had to pretty much, I don't know, I'm going back a long time now, but just as I was leading that, they brought in a whole lot of OH&S regulations, occupational health and safety, about licensing, and certainly going through university you couldn't use one, and it was a hassle. I see Curtis up the back there nodding. He's saying yes, I'll have to probably go through that whole accreditation process every year, and you've got to lock it away and put a radioactive sign on your truck and everything else. Because you've got to carry it around, it's expensive, but it is a good rugged tool, and the reason it haven't gone away is because it's a good rugged tool. But it's not great for irrigation scheduling these days, because there are other tools that are better. But in certain parts of the country, there are still consultants that run around with these and take readings. You go up to the Pacific Northwest, up to Washington State. That is still what a lot of people use. There are consultants out there that come around every 2 days taking readings. So different parts of the world do different things. So here we are at a slide that looks remarkably similar to what Russ showed just 10 minutes ago. It's a capacitance sensor, so the AquaSpy probe. This one has 15 different sensors on it, and every sensor measures a continuous trace of soil moisture. And I'm going to tell you how to use this in the next session. But this is really what we're doing, is we're measuring the volume of soil at discrete depths. And one of the best advantages of capacitance probes is that they measure out in a flat zone. So think of it like a donut out from the tube. They don't go upwards or downwards, they go outwards. And so, in fact, if I just flip over to this next slide, you can see where those radio waves go. They go out in a really flat arc from the side of the tube. So when you can actually see when water hits a certain layer but not the one below it, and you can know with absolute clarity how deep water has gone in the soil. It's a huge advantage. You can also see, as we'll show you, where the roots are active. You get a characteristic signature, and you can see layer by layer where you've got active roots. So that's a really, really big advantage with capacitance probes, which is why they're so popular. The other thing is you're getting a continuous trace. So most companies will take a reading every 15 minutes or every 30 minutes, somewhere in there. You can join the dots together and watch the plant drink through the day. It's a continuous trace. Neutron Probe, one reading every 2 or 3 days. So yeah, the resolution is great. It's real time. You can start to measure with EC, start to track nutrients. We can apply irrigation templates, which I'm going to talk a lot about. Won't go into that right now. And once you learn how to read the graph, it is things really, there's a lot of information in there. And the beautiful thing is too, that I've got every day of the season mapped out. So I can come back in the winter time, I've got my yield, I've got my quality data, or I can now go, let's slice and dice this. Let's have a post-mortem on how I got to where I got to. And I can have a look and watch that pretty much every day through the season. Not pretty much, I can look at every day through that season, know how deep my roots were, what my stress level was, and I can start to craft this template to make sure that I capture all the good parts and I adjust for where I got things wrong. The biggest disadvantage for capacitance probes is that they are they've got a small sphere of influence. So really, and this is where I'm going with this, there's a paper that is hugely, it's probably the most referenced capacitance probe paper out there, where a guy did a really good study where he put a probe in a big, like a wedding cake, and he started shaving off parts around the outside and measuring the readings at the same moisture content, and looking at what the distance was versus the amount of reading. So out here, 18 centimeters, so you're pretty much, where are we? We're about 6 inches out. 15 centimeters is, yeah, so we're 7 inches out from the side of the probe. Not far, so we're only this far out from the side of the probe. 100% of the readings. as you go closer and closer and closer, as he was shaving it off, he got to a point where you're really only 2 inches out from the tube, and you are starting to really, well, most of the readings actually occur within that first 2 inches. So what it means is that you're only, while you're measuring out sideways from the tube, you're only measuring out 2 inches. So it's just like a donut in the soil. So if you picture a probe down there with a whole series of donuts going down, that's the volume of soil you're measuring. It's really small, and as long as you understand that, and you understand the placement is really critical because of the small volume of soil, then everything else is fine. But it just makes them incredibly precise, but not inherently accurate, just because of the small volume of soil. Soil doesn't wet up evenly. Soil wets up very unevenly. And so if you had a bucket of soil and you're measuring a huge volume, that sort of averages out all the wet and the dry parts, so you can be pretty accurate in terms of total water. But when you're measuring a really small part, you're measuring that from a slightly wetter part of the soil or a slightly drier part of the soil, and that's where the inaccuracy comes from. So just lock that away. The next thing, so installation is critical, what we're saying here too, because this is an older style probe that goes inside a plastic tube, so don't worry about that air gap, that doesn't matter. But it's what happens really, really close to the tube is also very, very critical. So you don't want any air gaps when you put a probe in, which is why we tend to use a slurry. So we'll dig a hole with an auger, and then we'll half fill the hole with mud, and then you push the probe into the mud, because the mud comes off all around the side, takes out the air gaps. That's why we do it, because if you have air gaps, it will wreck the readings. And so things will fill in over time, but there's not a lot of time between when you can put a probe in after emergence and when you want to be irrigating. So that's why we do it with a slurry. You modify that environment, sure, but you do it in a controlled way to get rid of air gaps. So anyone that's doing their own installations, just be really, really careful. With sandy soil, we need to collapse the sand back in around the probe using a lot of water and using a rod or a push probe to try and collapse the sand in and around the probe to get rid of that air gap.
Even with the slurry?
Sorry, no, well, in a sand you can't make a slurry, because if I mix up sand in a bucket with water, as soon as I go to pour it, it's all settled to the bottom. So a slurry, I guess by definition, by my definition anyways, anything where the soil will stay suspended in the mixture. So when I mix it up, it's going to stay muddy, not water and sand. If it does separate out, then you pretty much can't use a slurry. You have to try and use dry sand, try and get it in the crack around the probe when you first put it in. Even better, there are probes companies out there that make a tapered hole, and you can wedge the probe into the hole. So there's different ways of doing it. But yeah, installation is a really important part of it. Does that answer your question?
Mm-hmm.
So yeah, coming back, installation is critical due to the small sphere of influence. These are highly, highly, highly repeatable, which I've got a slide to tell you what I mean about that. But what we're looking at, because we're measuring a small volume of soil, we tend not to calibrate them so much. We can, but it's not necessary, because you can watch for some signatures in the data, as opposed to needing to actually worry about the numbers. But that said, the numbers are actually really nice if you've got a calibration, because they do tell you something as well. But beautiful vertical resolution. I know exactly where the water's gone, I know exactly where the roots are. And temporal is time. So you've got that whole season mapped out every day. Yeah, as we'll see, it's all in the shape of the graph. So this is a slide that just summarizes everything. You've got it in the notes, we don't need to go on about it, other than you'd be surprised, I've actually said that the Neutron Probe scores really, really well for accuracy, whereas everything else scores, well, the capacitance probes are poor for accuracy, but for repeatability, it's the other way around. Capacitance probes are incredibly repeatable, but the neutron probes aren't. And so, what I mean by that, what's the difference between precision and repeatability? Well, think of it like sighting in a rifle. Okay, I've got a really high quality rifle that shoots dead straight. In fact, I don't remember which one I'm doing here. Oh, sorry. I've got I've got a really inaccurate rifle. Okay, it's an old lever action 30-30, and it shoots like a trajectory like a rainbow, and it's got open-sighted, and I'm having a hard time even hitting the target. But if I take enough shots, I'm going to be spraying them all around the target, and so when I average that, I'm going to be in the middle. Okay, that's what a Neutron Probe does. It's a rugged, blunt instrument, but if you take enough readings, you will average them and get to the middle. So that's why it's accurate, and that's why it's worth calibrating and stuff, but it just means you need to repeat the readings. So commercially, what we used to do was have 3 tubes in one field, and which is, you've got to go out there and take readings in this one, then readings in that one, and then readings in that one, and we'd average all 3 to get a value, and that's one monitoring site. And you're paying for someone like me as a summer intern going around there in a vehicle doing all this, so it was a slow job. Whereas a capacitance probe is like that straight shooting rifle. It'll put basically 3 shots, through a quarter at 100 yards. It's bang on. Trouble is, it's got a really fickle sight on it. It's got a scope, but you bump the scope and the scope's off, and so then you've got to sight it in again. So as long as you know where, it's probably not worth even trying to sight it in, just because you get it right for one soil. So what I'm talking about here is a calibration. If I calibrate it for this soil, and I take it over to that one, it's going to be off. If I calibrate it for this, and even if I put the probe in and I take the probe out of the ground, and then I put it back in the same hole and slurry it in again, it's going to sit just slightly differently in the hole, and it's going to give you a slightly different reading. So once it's in, as long as you don't touch it, it's gold, because we know exactly what that reference point. So it's like taking that first shot. I only need to take one, and I know that the way this is, I can get back through that same hole every time. I know exactly where to go from there. So that's why we talk about using a relative measure. So when we're looking at one against a measurement against itself, just at a different point in time, it's sort of why you don't compare numbers from that probe to this probe, because they're going to be slightly different because of the sensitivity of the installation. Any questions on that? Because it's sort of important to understand with capacitance probes. Good. So matrix potential, on the other hand, is this big fuzzy picture. So you've got fuzzy pictures that that are sort of over the top of each other, and that's why they just take a long time to generate, and you can't be really precise. But it's a good tool because they're cheap. That's why a lot of people use watermark sensors. A little bit I mentioned about what we're doing. So slip in a quick advert here. We're taking a capacitance probe. We don't make capacitance probes. We're using aftermarket capacitance probe. And Russ, if you want to sell one, we can do that too. But I know Aquasplay doesn't. So, but what we're doing is we're connecting it to a power, like a logger and a battery and a little transmitter, and it's transmitting from below the ground. Same technology, just different. It's a new way of using it. So then we're connecting that to an above ground repeater, and so this is wireless for about 30 feet. And so you can take the repeater away, you can farm over the top of it, and then you can bring it back and keep going. So yes, there is a spot here. We've got to go below the till depth. So it's there's going to be a part of the soil that we're not measuring, but as a lot of people have told me, I can dig a hole a foot deep. I just don't know what's going on 3 and 4 and 5 feet down, because that's really important, getting water down, and that's the part that's going to actually be your profit right there, which we'll talk about in the next session. So, but we can actually come and put another sensor in here for the season. But this goes in, and at the moment we've got a 5-year battery life, but we actually are going to develop potentially a drone strategy where you don't have anything out there in the field. You can just have a drone come out and pick up the data and move on. So it's almost back to like when I was a summer intern going around collecting data, except this is automatic. So anyway, that's something that's way down the track. This is where we are right now today. So we've started putting those out. That's what's brought me back to the area.
With the drone, will it just read when you fly over it?
Yeah, so it's not live. So you've got to send it out, 4 in the morning on it'll all be automated. I mean, technology exists, the licensing, the law hasn't caught up with that, because these days they still like someone to be on the other end of the drone within eyesight. So but there are plenty of drones available that could take off from a charging pad, fly on a predetermined course and come back and land on the charging pad. It's already there, but it's just, you know, the licensing for that is not available. So anyway, this is just, as I said, it's great for me to be back here with you guys, back in the area. We're going to be demoing some of this gear this summer, and we'll hear more about it as time goes on, probably the Emerald time shot. But essentially, taking data back, by having a capacitance probe in permanently, you can then start to potentially join the loop back to irrigation controllers, because you're not moving it. I said moving it, every time you move it, you're resetting all your magic numbers. But if you put it in there and you leave it there, those magic numbers don't change. So now I've got the ability to connect it to a controller and start to get into this smart irrigation control. And we'll be working with Pivot Track on that. So next thing, how else do I measure irrigation? I can use evapotranspiration, so I use a weather station or weather data. Pat relies heavily on ET for what he's doing with modelling. And what I'll say is that measurement tells you where you've been, modelling tells you where you're going. And so models are really, really important to plan. And so by what ETO, you might hear of, you know, what all these different numbers, ET, ETO, ETC. Well, ET, evapotranspiration, ETO is basically a well-known formula to simulate what grass, well-watered, well-drained, mown grass uses. And that is the reference to evapotranspiration. And so to measure that, basically they measured all the weather parameters and actually had grass growing on a big scale in a lysimeter. And so you can physically weigh the amount of water that's driven off there, and you can benchmark your, calibrate your model. Been around since, I mean, we talk about it, there's a Penman-Monteith equation, famous paper that was put out by the Food and Agricultural Organization. It's the reference, and then lots of people have adapted it from there. But it's certainly not new, it's robust, and people use it absolutely. I mean, here in this area, people live and die by ET, and talking then about what's my crop ET? Well, I'm taking what grass would use, and then I'm applying a factor that says this is what this crop at this stage would use. Sometimes it's less than what grass would use, or sometimes it's more than what grass would use. But you essentially have a model that for a certain period of time I'm using a certain crop coefficient, and then I change that crop coefficient to a different coefficient later in the crop cycle, the life cycle, when it's bigger and it's using more water. So, but what that does is, if I know how much water I've got right now today available in that stored soil moisture, or soil moisture store, and I say, okay, I've got 2 inches available, and then I look at my crop model, and I say that the weather data for the next 7 days is X, I can calculate my potential evapotranspiration. So use my crop model to say, okay, I think the crop's going to use 0.4 inches per day, and I've got 2 inches available, so I've got 5 days of stored soil moisture. That's how you use it to look ahead. So it's not rocket science, but it's essentially, with the analogy of the gas gauge and the trip computer. Gas gauge, I've got so much. Trip computer says I'm using it at so many miles per gallon, and therefore I've got so many miles until I'm empty. That's it. Sensor placement. So, yeah, so here we have, so where you put a sensor in the field, if I've got a 120 acre pivot, and I'm putting one sensor out there, I better be really careful where I put it. It's got to represent the whole rest of the field. And so people always ask, how many sensors do I need? Well, it depends on how many decisions you're trying to make. So if I make one decision for this circle, I'm going to put 1 inch of water out or 2 inches of water or whatever, but the whole circle gets it, I need one sensor, one probe to make that decision. If I'm trying to, I mean, if I split that and I've got 2 crops, then I'm going to make 2 decisions. So theory says you need 2 probes, but it's just like an air conditioner. In this building, if there's one air conditioner, there's only one thermostat. You just got to put the thermostat in the place where it makes the most sense for the most period of time, right? Where am I living? But if I've got 2 or 3 air conditioners, I've got one for this room, then I have a thermostat in this room, and a thermostat in another room, and a thermostat in a different room. So in my house, I've got 2 stories plus a basement, but I've got one system, so my thermostat's on the main level where we live, but it means that upstairs is either too hot or too cold, and the same with downstairs. And so you just have to live with that. And so that's the same with probes and how many you need. So first thing I'm going to do is look at soil. I had to pan right back. This is pretty much just down the road. The Sherm facility clay loam, I believe that is. You can see how many basically square miles there are with the one soil type. So you look at that soil map and go, well, that doesn't tell me anything in this particular area in terms of what's my variability, because it's the same soil type. So you could go to other systems like an EM, electromagnetic resonance survey, using Veris or other EM38 sensors. Essentially, think of it like a big soil moisture sensor that you drag up and down the field, and we're measuring any changes in moisture content should be due to soil water holding capacity. You have to be a little careful when you do it. If you've been irrigating, not a good time. You want to do it after rainfall, where you assume everything's had the same amount of water, and then you can, any differences are due to soil type. So we can see here that where I've got the lighter colours, or the redder colours, it's actually a lighter soil. So there is a band running through there, even though it's the same soil type. So depends on what you're trying to do, how precise you really want to be, but EM surveys will really work. I mean, you could do a grid survey, there are people that do zone surveys and all sorts of things, but putting your sensors in the right part of the field to manage the major, think of it like a bell curve in population distribution. So I've got that beautiful shape of a curve, and I want to try and be right in the middle so that I'm representing the most area under that graph. So, but if I am worried about running out of water because I'm growing corn, maybe I'll go in take one step to the lighter side and go in a slightly lighter soil, because if I can keep enough water up to that, then everything else, the majority will be wetter and okay. If I am worried about putting on too much water, then I'm going to go in a slightly heavier soil type, because if I back off of that, everything else will be a little drier. So you can influence the results. It's sort of more for an advanced user, but normally you try and go in the majority soil type. So that's looking at the EM survey. This little black area here is looking at it's taking elevation into account. So it's here it's all dead flat. I mean, I say dead flat, it's not, but elevation changes are not our problem generally here, not like going to the sandhills in Nebraska or a lot of other parts of the country. But elevation does matter, and so you don't want to be where water gathers, you don't want to be where water runs off, you want to try and be in a representative part of the field as far as water is concerned as well. So this is essentially saying, well, where this black area is actually the intersection of the average slope and the average soil type, and so I can put a probe anywhere in there. And this actually happens to be from a pin placement from one of the groundwater trials that we did. Looks like it was a 212 program, I'm going to say in about 2012. Micro placement, really important. So where do we put it in relation to the irrigation? You've got to think about, where does the water go? If I'm expecting the water to be even, is it? Like out along a pivot? I almost guarantee you that it's not, because nozzles wear out, and yeah, so you've got to sort of think, okay, I'm putting water on in a certain way, and I'm expecting every nozzle to be the same. Are they really? Because it does matter. And then also, how does that change through the season with canopy growing up and stopping water moving if I'm sprinkling it, that sort of thing. So we've got to think about, where do we place these probes in relation to the plants as well. So, and then of course there's just other operations. You want to get it out of the way of sprayers and things, because you're going to have potentially something sticking up in the field, which is your transmitter, your telemetry. So when it comes to wetting patterns, I mean, we've got everything from bubble to spray, these LDN, low drift nozzles. to drag, or the dragon line, but dragging a drip hose along the ground. They're all going to have a different wetting pattern. This was something that was done down near Lubbock, or down near Plainview, and they looked at different wetting patterns. And I'm not going to go into all the results. I'm just going to mention that where we placed the probe mattered in relation to where the water went. So here you've got the same kind of irrigation, one on 40-inch centres and one on 80-inch centres. So on 80-inch centres, I'm going to have dry middles and wet. I'm going to have, there's more water going, the same volume of water, just different application. So here I'm spreading it evenly. Here I've got a really wet part and a really dry part. So that matters. And that's why it's good to use somebody with soil moisture sensors that knows about this. And so certainly, with AquaSpy and wherever I've been, we teach this, and it's important to know. With spray, you're wetting all the ground, but not very deep. So it's a different type of wetting pattern. And what do I mean by this? Well, here is some probe data, and I've got this little upside down because I'll teach you how to read probe data in the next session. But if you just focus on this green line here, right? Here we are, we're wetting the green line, which only happens to be 4 inches down, and this red line, the blue line, at 8 inches down, isn't wetting up. And suddenly, you get water that goes all the way down, and it goes pretty much all the way through to this, very much the orange line here at 20 inches down, or 24 inches down. And then you get another shallow one, and some more shallow ones, and another big one. What the hell's going on? Well, they are rainfall events. And guess what? Rain has gone all the way down into the soil. And these are irrigation events. And so why are we getting differences? Well, it's because of the different application, why we're applying water. What's happening in the corn canopy is that the rainfall, right, is pulling water into the base of the plant. And yet there's an umbrella effect out here in the middle. So it's concentrating the water to the base of the plant. And guess where we put the probe? At the base of the plant. With the irrigation, it was basically had a nozzle that dropped down here and was putting a lot of water out in the middle, not on the sides. So by the time our probe over here wasn't registering all the water that was put on. Well, guess where the water was going? This was a no-till field, and holding on to last year's corn stalks and shifting over 15 inches and planting again. The water was being put on in the middle, and there were corn stalks there, and the water was going straight down the old corn, the roots that were rotting out on the old corn stalks. It was a sink. It's where all that water was draining to, and yet we had our probe over out to the side here, 15 inches away. 15 inches, mate, if I back that up, was the difference between what you saw here versus what you saw over there. So what that told me is that, man, this guy has a beautiful soil structure. He's just sucking all that water in by holding onto last year's corn stalks. Big tick. What it also told me is that we needed to put the probe where the water goes. So needed to put another probe in right in the middle, and where the sprinkler was. And guess what? So it starts a little later because we put it in after the season started. So they're the rainfall events, and these are the irrigation events. Big difference. So when it comes to putting water on, I can skip over this. This is really down around Lubbock, but furrow diking in cotton, it works. But if you put a probe against one of these dikes, you're not going to see the same information as if you moved it adjacent to where the water is ponding. And if you have a probe out in the middle here, you're going to get a different result to if you have it in the plant line. And the plant grows its roots across and intercepts the water, or it can do, before it actually subs out and hits the probe. And so we did some studies to put a probe right in the middle, one halfway and one in the halfway from the middle to the plant line. And what you saw were differences. Here we are right out on the plant line, away from where the water is applied. Here we are right in the furrow where the water is applied. And really here, top sensor, next sensor, by the time you get to the third sensor, nothing. Here we're going third, fourth, fifth, sixth, seventh sensor down is where that water's going.
So if you're on a spray mode, starting out the season, getting everything incorporated and all that, and then later in the season you go to a bubble mode, would that change?
That's fine, because the roots will find the water, okay? Plant will always find the water, but the probe can't move to find the water. And you've got to also think that the plant's going to grow across to where the water is, and it's going to stop it at the start of the season. The water might be making it all the way across to where the probe is, but later in the season, when the plant's big and the demand is high and the roots are massive, it's going to intercept that water and stop you seeing the wetting. So it's going to look like your irrigations are going less and less and less. They're not. It's the same volume. It's just not traveling as far. So I'm not trying to scare you about, oh, why am I doing probes? It's too much hassle. I'm just trying to explain to you that precision matters. It's a precise tool and precision matters. Let's just skip over this because that's the same. A little bit of water seen here, lots of water seen there, and this is the same. Those probes are literally 15 inches apart. Same with buried drip. If you have a dripper under the plant line versus a dripper between the plant line, wetting patterns change. These roots will grow across, so we can't have the probe. If I had the probe in the plant line, I could guarantee you later in the season that will be dry. You will not see the water. It won't make it across there. So we've got to put the probe closer to where the water is. Same with over here. If I've got tape under the plant, I can't put my probe in the plant line because I'm going to hit the tape. So it matters. We've got to find out where the emitters are. So we dig down and we work out whether this tape doesn't even run down the center of the bed. But find where the emitters are and then put the probe in very carefully in relation to where those emitters are. And here, this was actually some pigs growing in Australia, but it was some good data. This is where the buried drip tape goes, 4 inches away, 16 inches away. Here we are with the data. This one, when you're 4 inches away, we're seeing all these beautiful events. They're all irrigation events, and this was one rainfall event. When you're 16 inches away, I saw the rainfall and none of the other irrigations. So just like if I take a thermostat and I put it in a weird corner or shove it in a cupboard, it's not going to give me the same result as if I put it on the wall like this one is here in a place where we are where it gives you the most benefit. So time for a quick stretch the legs. I think are we on track? 5 minutes. Do we roll straight in? I don't know. With Steve.